In example one, you're using these two graphs to evaluate the limits. So F is the pink graph and G is the blue graph. Here in example A, we see that we are approaching -2 on the x-axis, and we're going to look at the pink graph plus 5 times the blue graph. So we're going to have the limit of F at -2. So we go -2. The pink limit would be 1, the open circle. So we've got a 1 here, plus 5 times the limit at G. So we go to -2 on the x again. We go down to G and we have -1. So we plug in or substitute a -1 in for that. So it'll be 1 plus 5 times -1. And so we're going to get 1 minus 5, which is -4. For B, you are approaching the limit at 1. So you're going to go to +1 on the x-axis. And you've got the limit at 1 for F is 2. And the limit at 1 for G does not exist because it goes to two different values. So here the overall limit does not exist because part of it does not exist. C, you've got the limit as x approaches 2. So you look at your F at 2, and it is about 1.5. And then you look at your limit as x approaches 2 for G, and that is 0. And so we've got 1.5 divided by 0. And so you would say the limit does not exist because it's undefined. In example 2, all you're going to do is evaluate the limits using direct substitution. So you're going to plug in 5 for the x's, and over here you're going to plug in -2. So go ahead and try that, and then pause the video and then check with the answers that I get. So for example A, I plugged in 5. I substituted in the limit for each of the x values, and I ended up getting 25 times 2, 3 times 5, and 4, which adds up to 39. Same thing for B, substitute -2 in for all of your x values. You end up getting -8, +8, -1, and on the bottom 5 plus 6, and so you should end up with a value of -111. Example 3, if you want to pause the video and try this on your own first. Otherwise, you're going to plug in 1 for your x values, and you'll see that you get 0 divided by 0. Now, you cannot divide by 0, so you have to do everything in your power to try to simplify the function so that you can plug in the limit and try to evaluate it. Sometimes you'll be able to, sometimes you won't. So in this case, we can simplify it by factoring the top. So let's do that now. What we can do is factor the top because it's a difference of two squares. So that'll factor into x plus 1, x minus 1. What this allows us to do is cancel the bottom factor. And so now we don't have that issue where we have 0 in the denominator. And we can go ahead and plug our limit in for the remaining expression. So we end up just having 1 plugged in for x, which just gives us 1 plus 1. And we end up getting an answer of 2 for the limit. Example 5, if you want to go ahead and try to evaluate it on your own, pause the video. Otherwise, if we plug in 0, we end up getting 0 divided by 0 again, which is an issue, and we want to try to do everything we can algebraically to simplify this to something we can actually plug in 0 to. So let's try that. On top, it looks like we can FOIL that parentheses, so we're going to split it into two parentheses. And then go ahead and FOIL. So we're going to have 9 plus 3h plus 3h plus h squared. And then collect like terms, your 9's cancel. So we've got 6h plus h squared over h. So we've done some algebra. Now you want to see, can you plug in 0 now? And you still get 0 divided by 0. So we still have some work to do. Looks like on top we can factor out an h. Now those h's cancel and we're not going to have 0 in the denominator, which means we can plug 0 in. We get 6 plus 0, which is 6. Try direct substitution to begin with. If you plug in -4, you're going to end up getting 0 divided by 0 again. So we need to do some algebra, some arithmetic, and see if we can simplify this. What I'm going to try to do is get common denominators on the top. So we're going to give this one an x and this fraction a 4. And that will give me x plus 4 on top over common denominator 4x over the denominator that we haven't touched yet, 4 plus x. What we can do with the denominator, we can treat this like a fraction and then give this a 1, and we're dividing by another fraction. So what you want to do is multiply by your reciprocal. And I'm going to switch around my 4 plus x and make it x plus 4, just so it looks like the top. And we can see that the top factors cancel. And so we end up with the limit as x approaches -4 of 1 over 4x. And now we can plug in our -4, and we end up getting -1 over 16. Go ahead and pause the video and try example 6. If you've already tried it, you'll see that you get 0 divided by 0 again. So in this one, we're going to multiply by the conjugate in order to get rid of the 0 in the denominator. So we're going to take the top that has the radical in it, and we're going to multiply by the conjugate. So you're going to leave your first term alone, and then change the 3 to a positive 3 for the conjugate. If you're multiplying that by the top, you have to keep your fraction balanced, so you're going to have to do the same thing to the bottom. Then you're going to FOIL, so you're going to distribute that. And you're going to have radical times a radical, which just leaves the inside terms but cancels the radical. Then you're going to have 3 times your radical. Then you're going to have -3 times your radical. Those middle terms are always going to cancel when you're using the conjugate, so you can waste time and not even do them. And then you're going to have last times last, which is going to be -9. On the bottom, I don't recommend distributing anything because we're going to end up canceling things, and it's going to be a waste of time to distribute or do any work in the denominator. So then what we see on top when we distribute, or when we collect like terms, is that the 9's cancel. Once the 9's cancel, the only term we have in the numerator is t squared. It's not being added or subtracted to anything. This is all we have left. So it will cancel with the bottom t squared. So that leaves a 1 on top. So don't forget, this is still a fraction, and the only stuff we have left is in the denominator, which means the numerator must be 1. So this is what we have now. Now we're going to try plugging in 0 again. So we have 1 over 0 plus 9. So we're going to get square root of 9, which is 3. 1 over 3 plus 3 is 1/6, and that is the limit. Example 7, show that the limit as x approaches 0 of absolute value x equals 0. You can do this several ways. I'm going to go ahead and look at it by definition, look at it graphically, and look at it using a table. So let's do that now. So this is how the absolute value function is defined by definition. So if we have a negative value in the absolute value takes that negative and turns it positive. So that's what we see here. If x is negative, if it's less than 0, then we take the negative, we add a negative to it, we'll multiply by a negative, and that turns it positive. So this is what the function does. If the value inside is 0, the answer ends up being 0. If the answer inside, or if the number inside the absolute values is positive or greater than 0, you just leave it alone. So the function does nothing. So the x stays itself. So using this definition, let's look at the limit at 0. So we don't really care what happens at 0. We care what happens to the left of 0 and to the right of 0. So we're looking at one-sided limits. So if I look at 0 from the left for absolute value x, we can see that to the left of 0, we get negative x. So if I plug 0 into that part of the function, I get negative 0, which is 0. Let's look at the function from the right. So not at 0, but to the right of 0, which means right here, greater than 0. So if I plug in 0 to the right side, I just get 0, which is 0. Since the left and the right agree, the limit at 0 is 0. This is a graph of the absolute value function. We can see from the left side, these y values are going down towards 0, and from the right side, these y values are going down towards 0. That is why the limit is at 0. Looking at a table, here I picked some values to the left of 0 and some values to the right of 0, and we can see from the left side, it's getting smaller towards 0. From the right side, it's getting smaller towards 0. So we can also look at a table and see that the value of the limit would be 0. Example 8, prove that the limit as x approaches 0 of absolute value x divided by x does not exist. We're going to do this using one-sided limits. Let's start with our left-sided limit. So let's look back at our definition and see what happens when the x's are less than 0. When it's less than 0, we have negative x. So absolute value turns into negative x. So that's what we're going to do to our equation. This absolute value turns into negative x. Now these x's reduce, they cancel each other out, so we get negative 1 as our left-hand limit. Let's try the right-hand limit. So by definition, what happens when the x's are to the right of 0 or greater than 0? Well, by definition, the absolute value function turns into just x. The absolute value symbols drop when x is greater than 0. So that's what we're going to do. We will drop the absolute value. These x's cancel, and you get positive 1. Because the left-hand limit and the right-hand limit are not the same, the limit does not exist. So absolute value is a piecewise function. Let's look at this other piecewise function in example 4. They want us to find the limit as x approaches 1. When you have a piecewise function that is not inequalities, like greater than and less than, but instead there's an equal to and a not equal to, if you're evaluating the function, just the function, no limit, just the function, you want to know what happens when x equals 1. But if you're evaluating the limit, you don't care what happens at 1. You care what happens just to the left of 1 and just to the right of 1. So that means we look where x does not equal 1. And this is where you'll find your limits. So again, if you're looking for the function value, it's where it equals. If you're looking for the limit value, it's where it does not equal. So in this problem, you would take 1 and plug it into this piece. And so the limit is 2 at 1. Let's look at a graph of that and make sense of the problem. This is a graph of the piecewise function that was just defined to us. So we've got the function is the line x plus 1, which is this line. But that's only when x does not equal 1, so that means we have a hole at 1. And then it said that the value of the function is pi, so 3.14, when the x value is 1. So that means that it's a removable discontinuity and the point has moved up to pi, just at 1. So when we evaluate the limit, we see that the left-hand side of this function is going towards 2, and the right-hand side of this function is going towards 2, even though it doesn't actually equal 2 there, but it approaches 2, and that's what we care about. So that's why the function value is pi